Hi, sixth graders. Today we're going to use what we have learned about proportions to be able to learn how to convert measurements. Now, you did some converting of measurements in fifth grade, but today we're going to focus solely on, okay, how do I use that knowledge about proportions and ratios to solve measurement conversions? So in our standard 6.RP.3d, it says, I can use what I know about ratios to convert units of measurement. I can change units of measurement correctly when multiplying and dividing quantities. So we are going to use what we know about proportions. We know that those proportions are equal ratios that are set equivalent. Then we can cross multiply to solve for any missing value. So in conversions, if we know the original rate of conversion, then we can use that to convert it to any other measurement that we need to. So you're going to see unit rates that we are going to use along the way. And we know that a unit rate is when the first quantity, we say how much the first quantity is in one of the second quantity. That's what makes it a unit rate, because unit equals one. And we're going to utilize those unit rates to set up our proportions and solve for the conversion measurement that we need to find. So let's get started. In example 1, it says Debbie's pet bird has a mass of 125 grams. How many kilograms is the mass of the bird? Now, this is what we know, and we're going to use the method words, known, unknown. Remember, anytime you're setting up a ratio or a proportion, the order matters so much, okay? And whatever unit of measurement we put in the numerator, it has to be that way through the entire problem. And whatever unit of measurement we put in the denominator, it has to be that same throughout the entire problem. So when we look at this, we're going to put grams to kilograms because we're looking for kilograms and we're given grams. Now, in a proportion, unless it is a percent problem, the order doesn't matter as far as which one goes in the numerator and denominator, but it has to stay the same throughout the entire problem. I will say the only time that I see that as different is when it's a percent problem or when it is a unit rate using price or cost. Typically price and cost are always going to go in your numerator versus, and then whatever the unit is will go in the denominator. Okay, so we're going to use words, known, unknown, grams to kilograms, and this is what we know. We're given this. Sometimes there's going to be some conversion tables that you're going to need to memorize, but you'll know that from your class. And we know that 1 kilogram equals 1,000 grams. Now, if we write that as 1,000 grams is equal to 1 kilogram, then that is a unit rate because the denominator is 1. So we're going to use what we know, and this is what we're looking for. They told us, okay, well, if 1,000 grams is equal to 1 kilogram, then how much is 125 grams? How many kilograms is that equal to? We use that same rate, that first ratio. Now, we cross multiply to solve this problem. So we're going to say 1,000 times x, and we get 1,000x, and 125 times 1, and we get 125. Now, we're going to divide by 1,000 on both sides because we're using the inverse operation to get x, the variable, by itself. So we say 125 divided by 1,000. Now, if you'll notice, 125 divided by 1,000 is a fraction, a proper fraction, which means that it will turn into a decimal. That's something that you learned in 5th grade as well. So now 125 thousandths is our answer. And what I would like for you to pay attention to is now if we put that in our answer form, we would say, okay, 1,000 grams was equal to 1 kilogram, but 125 grams is equal to 125 thousandths of a kilogram. If you will look at this ratio, they make sense because the proportion makes sense. in this example, the numerator is greater than the denominator, and that makes sense because a gram is much smaller than a kilogram. And so it takes more grams to make a kilogram, okay? So when our kilogram decreased, our amount of grams decreased as well, and vice versa. When our amount of grams decreased, then our kilograms should also decrease. So this is just a way to make sure and say, okay, is it reasonable? And that's always a good question to ask yourself when you are finding any calculations in math. Is it reasonable? Does this make sense? So your final answer is 125 thousandths of a kilogram. That's your example. That's your answer to example 1. All right, let's go to example 2. The meteorite found near Portland, Oregon weighs 14 tons. How many pounds does the meteorite weigh? So we're going to go with words, known, unknown. We are converting pounds to tons and tons to pounds. So I just chose to put pounds in my numerator. What I know is this unit rate. I know that 2,000 pounds equals 1 ton. So I put that in known. And then I am looking for pounds, so that's where my variable comes in, for 14 tons. So I'm using words, known, unknown. Always use that for proportion unless you are using proportions to solve a percent problem. And you can refer back to our percent video to look at how that is set up as well. Okay, so now we cross multiply. 2,000 times 14 becomes 28,000. And 1 times x becomes 1x. Any number divided by 1 is itself, so x is equal to 28,000. So there are 28,000 pounds in 14 tons. Again, we can check for that reasonableness by saying, okay, if 2,000 pounds is equal to 1 ton, then now 28,000 pounds is equal to 14 tons. And again, this makes sense because it is a reasonable answer. But also, if I were to cross multiply, I would get equivalent values. So 28,000 times 1 is going to be equal to 28,000. And 2,000 times 14 is going to be 28,000. Proving that this proportion is in fact a proportion, that the ratios are equal. Another way to check your thinking is if I were to simplify 28,000 14ths, I would get 2,000. So that is a way that you can always check your thinking to make sure that the proportions you're creating in the end are actually proportions because they are equivalent ratios. Thanks.